All right, the last textbook problem I want to look at is problem 5. And in this problem, we have, again, we're starting with a triangle ABC. So I'm going to go ahead and draw that triangle. No assumptions about any of the angles, but we have a triangle ABC. And we have a vertex, we have a square PQRS inscribed in this triangle in such a way that vertices P and Q lie on sides A, B, and AC, and vertices R and S lie on BC. And when I name a quadrilateral, I have more than 3 vertices, and so the order that we state them matters. And so I could call this square PQRS, PSRQ, QPSR, RSPQ, but the important thing is that I'm naming the vertices in a cyclic manner. So PQRS. That's why I know R had to be the one on the right, S had to be the one on the left. All right, and so we want to express the length of the square's side. So remember, a square, all sides are equal. So PQ equals QR equals RS equals SP. So all sides are the same there. And so we want to express that length in terms of a, little a, and HA. Okay, well let's translate those. So generally speaking, when we're naming things in a triangle, we're going to use capital letters to indicate vertices. And we're going to use lowercase letters to indicate sides. And we'll use the same letter for an angle and its opposite side. So little a should be the same as the side opposite capital, the angle or vertex indicated by capital letter A. So in this case, little a is the same thing as side BC of our triangle. And H we typically use for height or altitude. And so HA is the altitude through vertex A. So I'm going to draw that altitude. Remember, an altitude or a height is always going to be at a right angle. And I'm going to name a couple of things here. I'll name this point. Ooh, there's some thunder. Hopefully I can finish this video before I lose power. So I'm going to name this point, say A1, and this point A2. So in this picture, HA is the same as A1, and we know again that A1 is perpendicular to side BC. Lightning. All right, so we know those things. All right, so just for sake of ease, so we don't get confused whether we're calling PQ, QR, SR, SP for our side length of a square, I'm going to let X be the side of the square. So that's equal to PQ. It's also equal to QR, equal RS, and equal to SP, right? So that's the side length of the square. Okay, so now we've got to figure out some ratios and things that we know based on similar triangles. All right, now we know a few things here, right? Because we have some parallels. So for instance, I know that these three things are all parallel. And because of that, we can use the side splitter theorem to set up some ratios for us. So for instance, I know that triangle APQ, so this little triangle at the top, oh, right, we also have those parallel. So I know triangle APQ is similar to my entire big triangle, for instance, triangle ABC. And, well, what else do we know? We know that that's a right angle, of course. We know that AA2 is perpendicular to PQ, right? If we have one line perpendicular to a pair of parallel sides, that it's necessarily perpendicular to the other. And so because, for instance, we have that relationship, we can say that the ratio of side PQ to BC is equal to the ratio of their altitudes. So AA2 to AA1. And, well, remember BC is our little a, so I can say PQ. Oh, actually, well, remember PQ is a side of our triangle, so I can say X over little a, and AA2, well, let's think about this. So AA1 is our height, drawn from A, right? And A1, A2 is going to be the same length as the side of our square. And so if AA1 is represented by HA, I'm going to get this little bit left over by taking that HA, so that whole height, minus A1, A2. So hopefully that makes sense. So I'm going to put a little note here that AA1 is really the same thing as AA2 plus A2A1. That's a statement that we use a lot called the betweenness of points theorem. And so this statement that A2 is HA minus X is really just a rearrangement of that theorem. So if you need to, pause and take a minute and make sure you can understand why I was able to replace this expression with this expression, because that's really the key here, right? Once you have the similar triangles and are able to set things up, it's replacing one symbolic expression with a more useful symbolic expression, right? So it's actually solving for what we're looking for. Because if I'm trying to express the square side, which we're calling x, in terms of A and HA, I don't want to have any of these vertices A, A1, A2, B, C, P, Q. I don't want to have any of those in my equation. All right, so I'm going to take this last proportion that we wrote, and I'm going to cross multiply. So I have x times HA equals A times HA minus X. I'm going to distribute my A. I guess I can call it AX, whatever, it doesn't matter. and then, oops, not a sub x, a times x. So I'm trying to solve for x. So generally speaking, if I'm trying to solve for a variable in a linear equation, I want to get all instances of that variable onto one side of the equation. So I'm going to move ax over to the left. And so that's going to give me xha plus ax equals aha. Now I can factor out an x, which leaves me with ha plus a. Tablet's not behaving well. I'm almost done. And then finally, I can divide both sides by ha plus a, and I get that x is equal to a times ha over h sub a, or ha, plus a. And we have it.